All right, so it's 1:40. So it's my pleasure to introduce Laura Colmenarejo from UMass Amherst, who's going to tell us something about insertion algorithms for diagram algebras.
So thank you very much. Thank you very much for organizing this. It's really nice to have still the Discrete Math Day. Some of you may have heard a talk that I gave a year ago talking about insertion algorithms. So the beginning is a little bit similar, but then I want to get into diagram algebras. I can tell you that the paper is already published in the Journal of Algebra, and that you can download it for free before June. They sent us the link this week. And this is a joint work with Rosa Orellana, Franco Saliora, Anna Schilling, and Mike Stavroki. And my idea is that I want to introduce you a little bit of what we are doing in the paper. So the first thing that we do is to go through what is an insertion algorithm from the combinatorial point of view. So the general idea is that what we call RSK give us a correspondence between our input and some pairs of combinatorial objects that are called tableaus. So what I have in my mind when I think about an RSK algorithm is that you give me a two-line array, and I will give you back a couple of tableaus that have the same shape. And the reason why it's called RSK is because it was done by three mathematics. Of them were doing a generalization of the previous one. So Robinson gave this for permutation, Stenfeld did it for words of a fixed length in an alphabet, and then Knowles generalized it to generalize permutation. So I wasn't sure if people knew what I was talking about when I talk about partitions and tableaus, so I put a slide, a quick one. So a partition is just a sequence of positive integers that are quickly decreasing. And I'm going to say that it's a partition of n if the sum of all the entries is n, and it has length 4 if I have 4 non-zero entries. One way to visualize this partition is using a diagram, and I'm using, I think it's French notation. I have 4 rows, and then 2, and then 1, 1, like it's in this case. And what I'm going to do is I'm going to consider fill-ins of this diagram. And I'm going to fill them with numbers initially, and then set of numbers. And it's going to be a standard or semi-standard if I'm allowing to repeat entries or not. So this one is the standard with the entries 1 up to 8. And the condition is that I have to be increasing in the rows when I go from left to right, and in the columns when I'm going from bottom to top. If I'm doing semi-standard, I'm going to allow repetitions on the row, but not on the column. Okay. So what is the RSK insertion procedure? I want to define it in a more general way, but just with numbers. So I'm going to give you 2 alphabets, and I have to give you a total order in this case. And then I'm going to give you a generalized permutation, which is going to be a 2 array, in which I'm going to order the array by the top row. So in this case, you see that I have A, then the B's, then the C's, and the D's. And I don't have any order on the bottom. So every 2 components is going to be ordered by the top row. And I'm going to insert this. So I have some rules when I'm inserting, because what I want to get are tableaus, and I have to follow this condition that it has to be increasing in rows and columns. So I'm going to start I'm going to insert the bottom, and I'm going to record the top one. So I start with empty, and then I insert the X and record the A. And now when I insert the Y, that is my second column here, X is smaller than Y, so I can just put it next to it. And I record the B. I can do the same with Z, because it's still larger than Y, and I record another B, because it's the B that I have here. Now what happened when I insert W? It turned out that W is smaller than X. So it's like in my mind is I'm taking X and I'm putting it outside, and now I'm forgetting about the first row, and I'm inserting it in the second row. Since I don't have anything, I just put it there. And I record the C where I put the X. When I try to do it with the Y is smaller than the Z here, this one. So I'm going to put the Y in the position of the Z, and the Z is going to the second row. since Z is larger than X, I can just put it next to it. And I continue doing this. So there will be a moment, I think in this one, yeah, with the W. Well, the W is smaller than the Y here. So I will just put the W here and bump the Y. When I try to put the Y in the second row, it's smaller than Z. So I bump that Z and put the Y here. And now I'm looking to the third row. So that's the way that the columns are increasing when I find something that is smaller. And when I do the last part, I will get two tableaus with the same shape, and they are perfectly like ordered in the, like they're increasing or weakly increasing in the rows and increasing in the columns. And that is more or less the RSK, like in general, the RSK insertion procedure. So why are these algorithms interesting? Well, from the numerative perspective, they help us to prove enumerative results. And I will give a taste of that in a minute. And it's also related to Cauchy formulas. They are also connected with representation theory, in particular with the reducible representations and the dimensions. And I'm recently learning about insertion algorithm for partial orders, because the relation with chromatic polynomials, the Logan talked before. So during this talk, all our orders are total, so we don't have to worry about it. So what I'm writing here is a little bit of numerative results and to representation theory. So this was the result, the permutation of the symmetric group, and this part over here, which are the tableaux. I'm just using the usual notation. So the numerative result is giving us that the n factorial equals then the sum over all the possible partitions that I have of the number of tableaux that I have in each case. So since we have a one-to-one correspondence, I have this equality. I also have the same when I do it for extensive. Instead of having permutations, now I'm allowing to have words in an alphabet, so that would be k to the n, and I'm changing just this part because of what I have on the right side. And the more general case, I haven't included the formula here because it was very big, but it's giving us a nice description in terms of the number of these two sets of this product of binomials coefficient. Now, if I look at the representation theory, I don't know if you're familiar with it, but in the case of Robinson, this was a result for the group algebra of the symmetric group. This is related to the algebras, the group action of the general linear group and the symmetric group. And we also have the same here, the action of the general linear group, in this case in both sides. So this part over here is telling us what is the decomposition into irreducible. So what we did in this paper was to introduce a new perspective, because we wanted to do it for sets. So for multi-generalization from 6 to 5. So on the top row, I have entries from 1 up to 6. And on the bottom, I will have entries from 1 up to 5. So what we will usually do, we will be inserting these columns, then further 1, then the 5, 5, and so on. What I want you to do is to change your mind to a multi-set perspective. So what I'm doing here is I'm looking to the bottom row. I'm recording the sets like that, like the number that appear on the top row that has the bottom row the number that I want. So for instance, if I look at 4, I will not have any, I don't have any 4 here, so I will record empty. If I look at 2, I will have a 2, 2 here, so I have a 2. And then here I have a 6, 2. So I will keep 2 and 6 correspond to 2. And so on. For instance, if you look at 1, I will have 1 here, then 3, then 4, and then 6. Now, in my initial generalized permutation, I had an order on the top row. The order that I have in this case is lexicographic order, which means the graded one. So which means that I will first give preference to like the size of the And then if I have two sets of the same size, like here, and record the multisets. And that turned out to be a very nice insertion that gave us some results. But it wasn't exactly what we were looking for, because it wasn't working as we wanted for a particular algebra. So it turns out that multiset partitions are related to the diagram algebra, the partition algebra. So that's what I want to show you now. So if you look at the partition algebra, I will not get into a lot of details of the algebra itself. So you're going to have the span over the complex numbers of partitions in two alphabets. So I will have K and K bar. Those are going to be my two alphabets of the same side, and they are disjoint. So an element here is just a partition of these two sets. Now I can have sets that have entries, regular entries and numbers with bars, or just entries with no bars, or just only bars numbers, and things like that. One of the nice things and why this algebra is called one of the diagrams of algebras is because these elements can be represented with diagrams. So what I do here, I will put the entries with no bars on top, the bar entries on the bottom, and then I will link things that have the same, that are in the same set here. Now, I will not worry too much about how I represent it. So I will just take a generic representation. Like what we did was, what is most common is just to make sure that you're not like just connecting everything. So in this case, I have 1, 2, and 4, which is like this here. And then I'm going to 2 bar and 5 bar. So I have also this. So this diagram over here is representing this partition algebra element. Now, you don't see here the n, and the n arises when you define the product operation on the partition algebra. But since we are not gonna show anything related to the product, I just like leave it on the side. The only thing that we need is that n is larger or equal than 2k. So in this case, the algebra is really simple, but it also has many other nice properties, and in particular, you can say that it is isomorphic to some endomorphisms related to the symmetry group, and that's why we wanted it like this. And it will show up in a moment, like when I give you some idea that we actually need n to be large. So what we wanted to do, we're contributing in a different way. So the first thing we're going to do is we are going to order our blocks by the last letter. So when you look at set of numbers and you compare them, what is important is not the size, is not lexicographical, it's just the larger element. So that's how you're going to order your set. And then when you look at the examples, there are going to be some sets that only have bars numbers, and ones that only have non-bar numbers. So for instance, here I have 7, 8, or here I have 1 bar and 9 bar. So we call this non-propagating blocks. So what I'm going to do when I have my partition, my set partition, I'm going to split it into like three parts. The propagating blocks that I can describe as an array. So here I'm going to take on the top row the multisets that contain non-bar numbers, and on the bottom the ones with bars. So if I have 2, 3, 4, and 4 bar and 5 bar, I will contribute with this element here. The same I have for 5 and 2 bar and 3 bar, which is this one. Now 1, 6, and 7, 8, and then 9 and 6 bar, this one. And now I will keep in my mind the ones that are non-propagating blocks for each of the set of the alphabet, the ones with bar and the ones with no bar. And the way that we are going to define our RSK algorithm in this case is that I'm going to first do the regular, the classical RSK for the propagating blocks. So for the array that I have over here, I'm going to use a regular regular RSK. So if I look at this one here, and I do a regular RSK, I'm going to get this 2. And now is when then I still need to include the non-propagating blocks. So what I'm going to do is I'm going to add a row of enough black, empty boxes, and then add the non-propagating blocks in this case. So the first one will have n minus p minus b, where b is the number of entries here. No, p is the number of entries here, and b is the number of non-propagating blocks. So I will just do it in such a way that I have in total n entries. And I do it in both cases. And it's not a problem that I don't have the same number of non-propagating blocks. That works perfectly. And here is where, for us, the n plays a role. So what I wanted to say is that, like, the good part of this algorithm is that it behaves very well with subalgebras. So there are different ways that you can define subalgebras into the partition algebra, and one of them is by putting some conditions over the diagrams that you get. Permutation, it means that all of them has to be linked one with one, or perfect matching. These are coming very, I think that from the perspective of graph theory. So for each of these subalgebras, what we did on our paper was to look at what happened with the insertion algorithm, and everything works perfectly. So there are 2 tables there in the paper. This one is the subalgebra, the diagrams that it corresponds, and this one is the dimension. And the other table is talking about the representation theory side that I haven't had much time to talk about. But that's more or less all I wanted to say. Thank you.
All right, great. Let's give Laura a quick round of applause.
Oh, very nice.
Yeah. So yeah, if there are any questions, I think it's fine to go ahead and unmute yourself and ask it. We have.
So I have a question. So, are there analogs like with maybe like the first, like the longest, like some statistics you can encode, like longest increasing subsequences? Like do some cases have these properties? Or?
We haven't looked at the properties like that kind of properties, because the subalgebras are mostly defined like with graph properties, like perfect matches and things like that. So we haven't looked at that kind of properties. But I assume like it would be like a regular RSK, that the length of the partition that you get of the tableau will give you the longer sequence. Here you will have it in the second one with non-propagating blocks.
Laura?
Yeah.
Maybe there's something like jeu de taquin for each of these algebras.
I don't know. So we were trying to understand how it's related with the isolating tableaus and everything. So there, like the paper contains a lot of references that are very like there is a lot of literature on the talking about partition algebra and algorithms. So we were more focused on understanding how are the different algorithms related.